Principles of Finance with Excel Modeling, copyright Lou Gaddis. Topic 8A, Risk Measurement, Stochastic Models, and Macros. In this topic, we're going to measure risk using earnings at risk and Monte Carlo simulation. We're also going to create and record some macros. So let's talk about the last topic where we ended off. When we think about the risk management process, we can call it the IMM process. You first identify the factors that affect the viability of your enterprise. You measure how the risks affect your cash flows or profitability, and then you choose to mitigate the risk. So in our last example, we talked about Todd Hoffman's excursion into the Klondike to find gold. So we talked about what are the factors that affected the viability of his enterprise. It's gold prices. It's the quantity of gold in the ground. It's fuel prices. And finally, we talk about an environmental issue. It's if there's a cold winter and the ground is too cold to remove the topsoil. So there's a lot of factors that affect the profitability and cash flows of the gold mine. And then we measured how those risks affect the viability of the firm. We talked about the worst and best case scenarios. We talked about hypothetical and historical scenarios. So I looked at a cold winter and I looked at the 1981 Paul Volcker Fed tightening, where they raised interest rates to lower inflation, which hurt the price of gold. We looked at factor sensitivities. We did data tables looking at how gold appreciation and gold content affected free cash flows and revenues and EBITDA. And we also did a break-even analysis where we said what level of gold depreciation will cause the firm to have negative cash flows. And now we're going to talk about stochastic measures, and we're going to talk about his earnings at risk and simulation. Once you have measured those exposures, then you could choose to, you can choose to accept the risk. Maybe you find the risk is just too small relative to the overall profitability. You can choose to lay off the risk, meaning they can just cease operations or choose not to go to the Klondike. You can also hedge the risk. You can hedge a risk using business decisions. An example might be, well, if you're worried about fuel prices appreciating, you could just buy all the fuel today and store it. That's called an inventory build. You can use core samples if you're worried about the gold content in the ground, and if there's too little gold, you're going to waste a lot of time. You can just spend a little bit of money and time today, do a few core samples, and get a sampling of how much gold's in the ground before you spend a month tearing up all the topsoil. And also, what we're going to talk about next time is we can enter into forward contracts or financial contracts that say guarantee the price of gold. You can go to an institution, say a Chicago Mercantile Exchange or a bank in New York, and say, I'd like to get a contract today to guarantee the price of gold in, say, 1 year. And lastly, you can just hold capital. Through all your analysis, you might say, there's a good chance I'm going to lose 100K. So what you can do is just make sure you have 100K sitting around. So you just hold capital, kind of a rainy day fund in case that bad event happens. But we're going to focus more on the stochastic measures. Now, what we did last time was I gave you, say, 50 years of gold prices. We had 50 appreciations or returns on gold. We found out the worst year was 1981 when Paul Volcker raised interest rates. That is this movement right here. That's the biggest percent change in gold prices in the last 50 years. And Todd Hoffman was sitting right about here, right about the peak of gold, trying to figure out, what's the risk. And we did this analysis. We specified a base case scenario where we think we're going to have cash flows of $118,000. We said worst case, 211. That worst case, if gold prices are down and the winter is long, meaning the summer season's short and fuel prices are up. We did the best case scenario where gold prices are up and fuel prices are down, and it's a warm summer and a short winter. And then we did hypothetical scenarios. What if there's a global boom? And I just hypothesized that if the economy is doing really well, people are going to move out of gold and into things like stocks, so stock prices will go down. But that might drive up fuel prices because these developing economies are going to be using more fuel. And then I did another hypothetical, a long winter. With a long winter and a shorter season, I estimated what those cash flows would be. And then I did a historical scenario, the 1981 Fed change. And so now we have a kind of a good idea of what the ranges and scenarios that could lead to a better or worse gold season. And then we did some key factor sensitivities. We said, well, what would happen to revenue EBITDA, free cash flows, if gold prices are plus or minus 20%. And then we did a two variable. What would happen to, say, just free cash flows? If gold is between 0.1 and 0.4 ounces per ton, and gold prices are up or down. You can see the best scenario is you have lots of gold and the gold prices are up. And then we did break-even analysis. What price of gold, in the spreadsheet right here, what price of gold leads this to be zero free cash flows? It turns out that is if gold prices are down 29%. I'm sorry, yeah, 29%. And how much gold do we need? Well, question is what does this value have to be to make the free cash flow zero? And it turns out to be 0.17 ounces. And then lastly, what appreciation of fuel will make our free cash flow zero? And it had to be 188%, so a big change in fuel. So now you have an idea of kind of what can go wrong and what are the critical values. Now the advantages of this scenario analysis we just did in this looking at the break-evens is it's better than a single point estimate. It's better than that base case. It gives us a range. It looks at different events and looks at both hypothetical and historical environments. Now the disadvantage of what we've done so far is we really don't know the likelihood of any of these scenarios. And so we don't know how likely it is that gold prices will go up, say 40% or 20%. We don't know how likely a cold winter is. So there's two ways to try to solve this. One way is when you specify your worst and best cases, you can specify a probability. So you can say it's a 50-year best case and a 50-year worst case. In other words, it's a 1 in 50-year event. So you can get historical data and see the worst percentage change in gold prices or fuel prices in the last 50 years. You can get the longest winter in the last 50 years. And you can kind of specify that if all these bad things happen, that would be our worst case in 50 years. Now, what would be even better if you got everything correlated? In other words, what if you had data for weather, fuel prices, and gold prices for the last 50 years? You would just find what was the worst combination of those events in the last 50 years. And you can call those the worst and best cases. Now, another way we're going to do that is through stochastic analysis. We're going to use stochastic measures, and those two measures we're going to talk about today are earnings at risk, also called cash flow at risk in our example here, and Monte Carlo simulation, named after the famous city that has all the casinos, Monte Carlo, in the south, near the south of France. So let's talk about earnings at risk, also called cash flow at risk for our purposes in Hoffman Gold Mine. EaR and CaR are stochastic measures. In other words, another word for stochastic is probabilistic. It's a probabilistic stochastic measure of worst case. All right. So what we're going to do is we're going to specify the probability or confidence interval for our worst case. Say we want a 1 in 50 years or 1 in 20 years. And we would like to know over what horizon. In this case, we're doing this analysis over 1 year. All right. So let's talk about the EaR. So the EaR-CaR, what we're going to look for is the 1 year 95% confidence interval CaR and EaR. And let's just, before I show you how to calculate it, let's just say that 1 year EaR-CaR is equal to $155,000. Let's talk about what that means. What that means is if we go back to our base case model, if I find my Hoffman model here, my base case is $118,000 as the base case free cash flows and earnings, profits. If I take that as my expected value, 118, if I told you that the EaR-CaR is equal to $155,000 with a 95% confidence interval and over 1 year, you could make this following statement, that we expect free cash flows to be $118,000. And if you're looking for a 95% confidence interval EaR, we're 95% confident that those cash flows or earnings will not be $155,000 less. So it's a measure of worst case. However, it's the 5% worst case event. So it's kind of weird how we talk about EaRs and CaRs. It's a confidence interval of 95%. Really means what is the 5% worst case outcome. And that 5% worst case outcome is we get $155,000 less than expected If we're expecting 118, that means there's a 5% chance cash flows could be $36,000 or negative $36,000 or less. So that's what it means. Now, how do we actually calculate what is the 5% worst case scenario for Hoffman? And we're just going to focus on one risk, and that one risk is gold appreciation. And what we're going to do, we're going to make a big assumption. We're going to say that gold changes are normally distributed, the bell-shaped curve. We're going to give it a mean. We're going to make our guess of our expected appreciation of gold is 2%, and we're going to measure the dispersion, the fatness of this bell curve. And the standard deviation we're going to use is 25%. If we make that assumption that the standard deviation of gold appreciations is 25% with an expected value of 2%. By the way, I'm going to calculate this based on historical data, and I'm just going to estimate this based on my best guess. But if we make the assumption that gold appreciations have a normal distribution and specify a mean and a standard deviation, we can calculate the probability of any particular outcome. So how do I get a 5% worst case? Well, I'm going to have to go to a Z table for standard deviations. All right, this is standard normal probabilities for z-scores. And what we can find is find the 95% confidence interval in the table. And and then we look at the z-value. The z is 1.6, and the second decimal point is 5. So this table tells us it's 1.65 is the z-value, which means there's only a 5% chance of having a 1.65 standard deviation from the expected value. Now again, the expected value is 2%. So there's a 5% chance that it could be 1.65 standard deviations less than the 2% expected appreciation. And if I use a standard deviation of 25%, I can just take 1.65 times 25%. Now you will never have to do a table in our modern world. As long as you have Excel, you can just use the function equals norm SINV. Plug in the confidence interval, 95%, which means you're looking for a 5% tail. All right, one tail test, and you'll get the value of 1.645. You can then use that and use our VAR formula. We're going to take the annualized standard deviation multiplied times my z, and we said that if x, the confidence interval, is 95%, z of x must be 1.645. I'm going to assume that my standard deviation is 25% based on historical data. I'm going to multiply that loss times 1 minus the tax rate. So again, we're talking about worst case losses. Any loss or lower income is going to create a tax shield. So we're going to take 1 minus the tax rate. And then lastly, I'm looking at a 1.65 standard deviation change in the value of my gold. Let's put in the current value of the gold. We're expected to mine 337.5 ounces of gold. The current spot price of gold today is $1,600. So the V in this equation is the current price of the expected gold or quantity of the good. So my V is $540,000. That $540,000, there's a 5% chance that I get 1.65 times 25% less. 1.65 times 25%, that's 41%. So there's a 5% chance I'm going to get 41% less than 540. And that's how the EaR and CaR is calculated. I just take my $540,000 times the standard deviation times my z of x, or x in this case is 95%, and I multiply times 1 minus my tax rate, and it tells me the 95% confidence interval 1 year EaR, I know it's 1 year because this is a 1 year standard deviation, is equal to $155,000. So again, the interpretation of the $155,000 is right here. There's a 5% chance that my cash flows will be and profits will be $155,000 less than expected. Another way of thinking about that is there's a 5% chance that I don't get my 2% expected appreciation. There's a 5% chance that it's going to be 41% less than expected, right? My Z times my sigma. So there's a 5% chance that gold prices are down 39, which is 41% less than 2. If that happens, I will lose $155,000 after tax. This is the EaR CaR. So that's the advantage of having an EaR CaR. You can talk about probabilities. I'm 95% confident losses will not exceed 155. However, there's a 5% chance that my cash flows and earnings will be $155,000 less than expected. All right, and the second advantage, so that's a big advantage for using EaR CaR. You can scale it through time. The second, you can get a probability. The second advantage is you can scale it across time. In other words, if I just take my annual standard deviation and plug it in this formula, this will always, as long as the standard deviation is annual, it will always give me a 1-year number. However, there's a square root rule for scaling volatilities. If I wanted to know how much money I can lose in, say, a day, I can take the annual standard deviation and all I do is make that into a daily standard deviation. How you scale standard deviations across time is you don't divide and multiply times time, you divide and multiply times the square root of time. And that comes from the calculation of standard deviation, which you remember is the square root of the variance, where variance is the average square deviation from the mean. So if I had the annual standard deviation and I wanted to know my 2-year EaR, I would just multiply times the square root of 2. If I wanted to know my 1-day EaR, I could divide by the square root of a number of business days in a year. Let's say it's 252. That will give me a 1-day standard deviation. If I wanted a 5-day standard deviation, I could take this 1-day standard deviation and multiply, say, the square root of 5. That will give me a 5-day. So this is the scaling rule for scaling standard deviations and EaR through time. My daily standard deviation would be the annual times the square root, or divided by the square root of 252, which is the same thing as multiplying times the square root of 1 over 252. I can also get a daily standard deviation by taking, say, the monthly standard deviation and multiplying times the square root of 1 over 21, assuming there's roughly 21 business days in a month. I can also get a monthly standard deviation if I start with an annual standard deviation by multiplying times the square root of 1/12. I can get a weekly standard deviation if I start with an annual standard deviation by multiplying times the square root of 1 over the number of weeks in a year. So let's go ahead and do a few of those calculations. If I have my data here, remember I got my worst case, was losing 25.26%. We can calculate E equals STDEV. That's my standard deviation. I'm going to select all of my appreciations, and I get a standard deviation of 25.01. That's why I used 25% as my standard deviation in my EaR. If I needed a daily standard deviation, I could take that and divide by the square root of 252, the number of business days in a year. And that would be 1.58%. I could also do it another way. I could just multiply times the square root of 1 over 252. That does the same thing. There's my 1.58%. If I had a daily standard deviation, I want to know the 1 month standard deviation, I can just take that and multiply times the square root of 21 business days in a year. So if you have any standard deviation measured over any time horizon, all right, again, this uses annual data, so it must be an annual standard deviation. You can scale that through time by using that square root rule for scaling volatilities. I can then use that to calculate my EaR. And here's a general EaR CaR formula for any t, any time horizon, and any confidence interval X. So let's make this model where you plug in a confidence interval, you plug in an annual standard deviation, you plug in your V, that's the expected quantity of the good you're trying to sell or buy, times the current spot price of that good. You plug in your tax rate, and here's the formula right here. First of all, you have to get one other calculation. You have to say equals norm S inverse of the X. Let's go to the file. Here's my general EaR. So here are my parameters. But the first thing I'm going to do is going to calculate if my X is 95%, my Z of X is norm S INV of the X. So there looks like there's a 1% chance of having a 1.6448 standard deviation, single-tailed statistic, if it's normally distributed. And then I can do my general EaR formula, where you take your V, your Z of X, 1.645, 1 minus my tax rate, my annualized standard deviation, and then multiply that annualized standard deviation times the square root of T over 252. So if I wanted a one-day EaR, say Todd is going to mine a certain amount of gold one day from now, what it basically would do is take this annualized standard deviation. Let's just assume this quantity is a one-day quantity. All right, we're expected to mine $540,000 worth of gold tomorrow. I could take that standard deviation and this formula. It's going to adjust this annual standard deviation to make it a daily standard deviation. So it's going to multiply times the square root of 1 over 252. That'll give me a one-day standard deviation. So there's a 5% chance they'll have $10,000 less tomorrow if they mine this amount of gold tomorrow. Now what I probably do is divide this by 252 and get kind of their daily gold quantity. All right, so now that's how to do EaR-CeR. It's a probabilistic measure of worst case. And if you specify 95% confidence interval, you're getting a 5% worst case after tax outcome based on that one variable. And that one variable in this case is gold appreciation. Let's talk about our second stochastic measures. That's going to be a Monte Carlo simulation. So again, stochastic analysis is an analysis where values are randomly determined using a probability distribution or pattern that can be analyzed statistically. So let's talk about Monte Carlo simulation in particular. It's a method to analyze a problem stochastically to help decision makers. And here are the steps to create a Monte Carlo financial simulation. The first thing you're going to do is create a model. We've been doing this since the first day we met. We just have a model that calculates something like net income, free cash flows, or NPV. For Todd Hoffman, we have a model that calculates free cash flows. So you have a model, at least one outcome, free cash flows. We've done that. And then we're going to select a key variable that we're going to say is randomly determined. And the one I'm going to pick for Todd Hoffman is gold appreciation. All right, so let's make gold prices random. All right, but random in a particular way. We're going to say they're going to be random. However, they're going to be random according to some kind of pattern. So we can say that gold prices are randomly distributed, but they're going to have this bell-shaped curve, this symmetric bell-shaped curve, which is associated, with the normal distribution. It is a picture of the normal distribution. However, we could say that the random gold prices have a triangle distribution, or we can say they have, say, a rectangular distribution or a uniform distribution. Or we can take some kind of a weird distribution that's not symmetric. We can have, say, a log normal distribution with kind of fat right tail and a thin left tail. But let's just assume, which is a common thing to do in finance, that the changes in prices or percentage changes in prices are normally distributed. What we're going to do is we're going to generate lots of different random gold prices based on our assumption of the pattern of gold prices, appreciations, and then we're going to generate, say, 10,000 of these random gold appreciations based on this curve, which will give us 10,000 different free cash flows, and then we're going to analyze the distribution of those 10,000 and see if it helps us make our decision. So let's go ahead and build this model. So we're going to go to the Monte Carlo tab, And here's our model that we've done in the last class. Here's our parameters: $200,000 labor, our equipment lease, number of days in the season. That determines how many days you actually get to mine. The amount of dirt you can mine in a day. The amount of dirt, total amount of dirt over the season. We determined that we're going to get on average 0.25 ounces of gold per ton of pay dirt. That gives us 338 ounces of gold. That's our expected quantity of gold. Current price of gold is $1,600. Diesel fuel, we're going to need 200 gallons a day. Current price of diesel fuel is $4.05. Diesel fuel appreciation is 2% and our tax rate is 30%. Based on that, and if we assume that gold prices appreciate 2%, gold prices will be 1,632 ounces or dollars per ounce, and then that generated our base case free cash flows and earnings in this case for Hoffman. There's our revenue, price of gold times the quantity of gold, our lease expense, our labor expense, our fuel expense. There's our EBITDA or EBITDA. No depreciation. We're going to get our earnings before tax, take out taxes, and there is our base case earnings. Now the question is, if we assume that gold prices are randomly distributed, could we create a model that generates, say, 10,000 possible gold appreciations? And that'll give us 10,000 possible free cash flows. And then how can we use that data to make a decision? Well, let's go ahead and do that. Before we do a random normal distribution, let's do something in Excel. Let's just say equals rand, open parenthesis and close or bracket. When I do that, Excel, and I'm going to keep hitting F9 to recalculate while I'm talking. Excel's rand function gives me random numbers between 0 and 1. It's a uniform distribution, meaning it's a flat distribution. Every number between 0 and 1 is equally likely to show up. So you just see lots of numbers between 0 and 1. However, we don't assume that gold prices are gold appreciation is between 0 and 100%. We have to transform this random 0-1 variable into a normal distribution variable with a 2% mean and a 25% standard deviation. The model we do that is with this model, this little formula right here. How we simulate a normal distribution is take the mean, say 2%, the mean appreciation, plus a random variable, a random z value, which is norm s inverse of this random 0-1 variable times the standard deviation. So what this means is we expect 2%. But we're going to have a random normal value show up here as our z times the standard deviation. So it's a random z value. So let's go ahead and change this formula from our deterministic 2% to 2% plus norm s inverse. That converts it into a random normal distribution. Put in this random 0-1 value. That's going to transform that number into a normal one and multiply times our expected standard deviation. Now every time I hit F9, this cell B22, those numbers have a mean of 2%. In other words, if I did 1,000,000 of these, the average would be 2%. And if I calculate the standard deviation of these 1,000,000 numbers, if I hit recalc 1,000,000 times and copy that number, the mean would be 2% and the standard deviation would be 25%. So this is my model, the way I model random prices of gold, or random appreciations of gold. Based on that random appreciation of gold, I have a random price of gold, which is simply the current spot price of gold times 1 plus that number above. So right here is a random appreciation of minus 11%. So gold prices are falling from $1,600 to $1,400. Here's a random, here we're supposed to do a couple more randoms. Here's a random appreciation of 30.32%. So in this random event, 1 year from now, say the price of gold is $2,000, and if the price of gold is $200,000, they make lots of free cash. Their free cash flows are high. I'll hit F9 again. That's a terrible outcome. There's a random outcome where gold is down 29% and cash flows are really low. So now what I'd like to do is basically hit F9 or get 10,000 possible appreciations of gold, and then I'd like to do is copy these 10,000. All right, I want to get 10,000 free cash flows, and I want to put them right here, and I want to then look at that column and see, you know, what's the largest and what's the smallest value and what's the expected value and how many of those outcomes are below 0 or above some high number. All right, but how we're going to do that, we can do it the hard way. The hard way is say copy the value and paste it here as a value. Once I paste a number in Excel, it automatically recalcs and gives me a new random number, and then I can copy that again and I'm going to paste it down as a value, 119, and there shows up 150. I'm going to copy that because I got a new random. I'm going to paste that as a value. Alt-HVV, by the way, is my shortcut. Alt-HVV, Alt Hector, Victor, Victor. So what I'd like to do is now do this 10,000 times and then look at the average and look at the median or anything I want to do. Let's graph it and we can think about the risks of doing business in the Klondike. However, let's talk about macros now. A macro is simply a VBA code that's executed. It's not inserted into the inserted like a formula, right? You don't insert a macro by doing insert function here. A macro is VBA code that's executed from the developer developer macros. If you have a macro, you just execute it by say clicking on it and hitting run. And here's the macro we're going to run. First of all, every macro can be is going to be written inside a module. It could be the same module which you have functions in it. So I think this spreadsheet has a function and modules inside module 1. Here's the macro we're going to talk about. Here's all macros start off with the word sub. Then we give the macro a name. I called it simulate 10,000. And then you do open and close parentheses. Now when you do open and close, that tells VBA that this is a macro besides the word sub. So you can say sub for subroutine, give it a name, and then put no parameters inside these brackets. And here's n sub. So here's what this program is going to do. I set up a counter for I equal to 1 to 10,000, next I. So it's going to set I equal to 1. It's going to execute this statement, come back to the next I. Come back here, set I equal to 2, the next value. Execute this statement, and go next I, set I equal to 3. So basically this program is going to set I equal to 1 to 10,000 and execute these two statements 10,000 times. Let's take a look at these two statements. The first thing I want to talk about is what is the cells command. The cells command in VBA is how it can put values in your spreadsheet. Cells 1-4 refers to the first row, fourth column of the active workbook. First row, fourth column is right here. It's actually D1. So it says put in D1, cells, first row, fourth column, the value of 10,000 minus I. So the first time it runs this, it's going to put right here 9,999. Let's forget that statement. Next I, it's going to set I equal to 2, and it's going to put in the same place cells I4, 10,000 minus 2, which is 9,998. So this is going to create this little piece of code. If I didn't have the next line there, we'd just do a countdown in D1. Now here's where the actual work's going to be done. This piece of code says put in cells 2 plus I 4. Now when I is equal to 1, 2 plus I is 3. So put in 3, 4, third row, fourth column, which is right here, D3. Put in D3, whatever's in cells 35-2. What's in cells 35-2? The 35th row and second column is right here. It's the actual free cash flow in B35. So we're going to put in the third row, whatever's in B35. Once it inserts it, Excel will just automatically do a recalculation like it always does when you hit enter. It's going to set I equal to 2. It's going to do the counter. And then it's going to do the cells command again. Except when I is equal to 2, this is going to be cells 2 plus 2, 4. In other words, fourth row, fourth column. It's going to put here whatever is in the free cash flow. So what's happening during this loop is this cell here is going to be a countdown from 10,000, well, from 9,999 down to 0. This cell is going to be whatever's sitting in free cash flow to start with. Then it's going to paste it there, and then it's going to grab the next one, and it's just going to start filling in random free cash flows. And every time it fills one in, and anytime you hit enter in Excel, say enter a value in Excel, I'll just enter the number 1 here. It's going to automatically recalc a random number here, which then generates a random gold appreciation here, which then creates a random gold price here. So all I need to do is execute these commands, this macro. Now I could just go developer, macro, and I could double click on simulate 10,000, but let me show you a different way to do it. You can attach any macro to an art object. So let me do insert. Let's go ahead and put an art object. I'll put a star. I'm going to right click on that star and click on assign macro. I'm going to assign it, simulate 10,000, and hit OK. Now when I click this, I'm going to zoom out a little bit. When I click this, by the way, this is a histogram that's starting to collect all this data and put it in a graph. When I click on this, it's going to start collecting free cash flows and start putting them down here and do a countdown. So let's go ahead and run it. All right, here's the countdown. I already have 1,000 random free cash flows. And there it goes. So what you don't see happening is every time it's just moving more data down. It's already done 2,000 free cash flows by generating 2,000 possible random numbers between 0 and 1, which creates 2,000 possible gold appreciations and then 2,000 possible free cash flows. Now I've done 3,000 of them. So we'll let this run, and then what we're going to do is take a look at the final distribution, and then we'll analyze the results. Okay, I took a little pause there. It looks like the distribution just finished. Here are my 10,000 outcomes. Here's a graph, a homemade histogram I did. All right, I created these separate bins, but on your assignments you don't have to do this. I just did this so it updated dynamically for me. And this is a beautiful picture of a bell-shaped curve showing the 10,000 free cash flows put in bins. In other words, there are 702 outcomes between 200 and 225, and 476 outcomes between 275 and 250, and so on. Looks like the most likely one, looks like, say, 150 is, say, the most likely outcome. That would be right about here. So this is the results of my Monte Carlo simulation. These are my 10,000 possible free cash flows graphed. So you can look like out of the 10,000, looks like there's almost over 1,000 in this about $150,000 bucket or bin. There's only about 200 outcomes that are in that $50,000 bin. There's about 200 outcomes in that $300,000 bin. Those bins are $25,000 range. So what could we use with this information for? The first thing I'm going to do, I'm going to highlight all of the numbers. I'm going to do Control-Shift down. I'm going to put in a named range of nums. Looks like I already did it. So I'm going to go back up. I'm going to hit my N button or my Control-Shift up. All right. So now, let's try that again. So now here are my 10,000 numbers, but I gave it a named range of nums. So let's take an average of all the numbers inside nums. The average is $119,000. Now yours will be a little bit different because you have a little bit different of those random 10,000 values. Now if we both did 1,000,000 values and not 10,000, well, I probably wouldn't see you for another week because this thing would be still running. But we'd all probably get a number really close to the base case. So 119 is really close to my base case of 118.9. And what I'm telling you is if we had 1,000,000 random numbers, we'd probably both get within $1 of this base case, because this model we're using, this normal distribution, is centered around the 2% appreciation of gold, and the normal distribution is symmetric. So I would expect the mean of this distribution to be right around 118.9. So that hasn't told us very much yet. But how are we going to do really interesting things like, of these 10,000 random free cash flows, I can get, say, the largest 5%. So I can use the large function in Excel, put in the name, or put in either the range, either actually type in the range, or put in the name range of nums, and I could ask for, say, the 500th largest value in that column. It's $274,000. So again, I'm starting to think about what are the risks and opportunities of doing business in the Klondike. And what it's telling me is kind of the 250th largest number, I'm sorry, the 500th largest number, which is 5% of 10,000, is 274, which is right about here. So what it's telling me is about 5% of the outcomes are greater than 274, but the 5% highest is about 274. I can copy that and use the small function. The smallest 500, in other words, if I sorted this column small to large, the smallest 500th is negative 36,000, which is right about here, negative 36,000. So what that tells me is about 5% of the outcomes are less than negative 36,000. 95% are greater than 36,000. If I take the difference between the average and the 5% lowest, I get, in my case, about $155,000, which, by the way, is exactly equal to my 252 one-year EaR. Right? Both these, the EaR and my simulation, are based on normal distributions. So I'd hope it actually gives me the same expected value. There's a 5% chance of having $155,000 less than expected. And that's what this Monte Carlo is telling me. But I can also do even more interesting things. We can calculate the probability that I break even, or the probability that cash flows are, say, less than 0. So I can say equals count if. I can put in my named range, and I can say count the number of times the cash flows are less than 0. That'll tell me how many are less than 0. If I divide that by the 10,000 outcomes, that'll tell me there's about a 10% chance of losing money. In other words, 10% of the outcomes are below 0. 90% of the outcomes are above 0. I could do the probability that I have a really good year. What's the probability that the cash flows are, say, greater than $250,000? And there's about an 8% chance that I can make more than $250,000. So this is what you can do with simulations. You could take a variable, say gold appreciation, assume normality, get the equation for that simulation, or for that distribution. For normal distributions, it's the mean plus norm S inverse of the random number, that random z, times the standard deviation. You can generate 10,000 possible outcomes, and then you can explore the distribution like I did here. Let me show you one other way you can run this normal distribution. Why don't I just put this formula inside a function? All right, well, I did. If I look at Alt F11 here, go to my VBA, here's a random normal distribution function. The function's called random normal. Parameters are mean, standard deviation, and random. Random's going to be, I'm going to have to insert the or make a link to the random variable, that 0, 1 random variable we created. And here the function just simply makes one simple calculation. The random normal is equal to the mean plus application.normS inverse random or normalized inverse random, multiplies times the standard deviation. So I could just insert this function instead of doing it myself. So in other words, I didn't have to do, I could have made this a function, and I could just insert the function, user defined, look for my random normal, put in a mean of say 2%, my best guess, a standard deviation of 25%, that is my based on historical data, and the random is just going to be this random 0, 1 value. And I hit OK, and I could rerun the function like this. Now it's going to give me roughly the same values as before as far as the distribution. So I'm going to hit escape twice and stop it. Now the reason I'm showing you is doing this function instead of actually doing the formula is I'm going to show you 3 other distributions you can use really easily. A second distribution is called a uniform distribution. A uniform distribution, the formula is actually quite simple. You just specify a min and a max, and it just simply generates random numbers between the min and the max. However, you don't specify a peak. So when you specify a uniform distribution, what you're saying is the distribution is going to look like a rectangle. So if I rerun I need a formula, and actually the formula turns out to be this formula here. The random uniform value is equal to the minimum, whatever you specify, plus that 0, 1 random number times the difference between the minimum and the maximum. So I can put in this function called random uniform right here. I'm going to delete this one. Let's delete this. And let's call this random normal. Random uniform. I just need a min. Let's just say we think the worst case is negative 40%. That's the worst case we expect. And the max, we expect the best case is maybe plus 40%. And then we can say that the random variable, that's that 0, 1 random, is right here. And now, every time I hit F9, I'm getting a random number right here between negative 40 and plus 40%. There's no central tendency, meaning that they're not going to be bunched up around 0 or bunched up around 2%. They're all equally likely. And then I could rerun the simulation, and then I'm going to have 10,000 free cash flows based on a uniform distribution. Now I'm going to stop it and just show you the picture because I don't want to wait for this, and show you what it's going to look like when you run it. It's going to look like the outcomes are going to be these, or look like these. These formulas still work, but when I graph them, it's going to look more like a rectangle. In other words, there's no central tendency like a normal distribution. So what I'm specifying is the distribution of price appreciations is no longer a bell-shaped curve, it's a rectangle. And all I have to specify is the max and the min in that little formula. The min plus the random number times the difference between min and max will tell me, will give me these random outcomes. And the last one I can do is a triangle, right? Why specify a bell, right? A triangle is a lot like a bell. It has a single peak. However, with a triangle, I can specify a min, a max, and a most likely, or the peak. And if I specify that, I can draw a triangle. Now with a normal distribution, you specify the peak, which is the mean, and the standard deviation is the width of the bell. So let's go ahead and put a triangular distribution in, and let's just pretend that the min is 40%, the max is min is negative 40%, max is 40%, and we can calculate a peak of say 15% or 2%, whatever we want it to do. So let's go ahead and do that. So I can just take out my random appreciation and my new uniform. Let's say it's going to be triangular distribution. And I have a function that calculates it. And you could look up this function to see how it's calculated, but I'll show you that it does work. Let me just get my random triangle. I specify a min, say negative 0.4, max 0.4, and I can do a peak, and I know I've been using 0.1, 0.02, but let's go ahead and do 0.15 for fun. Let's make it asymmetric. When I say asymmetric, I'm making the peak closer to this number. You know, it's not directly in the middle. Right in the middle here would be 0. So I'm actually making a triangle that's asymmetric. We'll take a look at it in a minute. Now the random number is still that 0, 1 random number. I could run this 10,000 times, but I'm going to stop it and show you the result. The result looks like this. And this is my asymmetric triangle. By specifying the mean is 15%, the max is 40, but the min is -40. What you're doing is creating an asymmetric distribution. And then based on that, we can get our averages and our 5% lower and our EaR based on that distribution. And our probability cash flows are less than 0. Probability cash flows are greater than 0.5%. Right? Notice there's almost no probability cash flows are greater than $250,000 because unlike a normal distribution, it has a limit, the limit of 40%. Normal distributions go on forever. Right? They get really thin, but they do go on forever. There's some probability of a really bad and really good event. So there we go. This is how to do good financial analysis and risk management. Specify your single base case, single point estimate. Do some best and worst case scenarios around that to kind of get an idea of what is the true range. Do some hypotheticals, global boom, 1981 historical scenario, a long winter. Do some data tables to talk about how different parameters are affected by the big value drivers. And then do say a two-factor data table looking at 2 factors. Do some break-even analysis. And then lastly, you can run some simulations and calculate things like your earnings at risk, which are also over here, and calculate your 5% largest and probability cash flows are less than 0. And now you really have a full picture of doing business in the Klondike. You can use this picture to figure out how much capital should I use or hold. In other words, this analysis might verify that I better hold $100,000 or $150,000 in capital. Or this analysis may determine that you shouldn't go. There's not as much upside as I'd like. All right, last thing we're going to do is we're going to spend a couple minutes talking about a couple other macro things. And that is macros can be created a different way, and that is they can be recorded. So let's go to our workbook, and let's go to the gold one. And just for fun, what if we said we always do a repetitive task in Excel, and we want a macro to do that repetitive task. So say every day you went to work, and for whatever reason you had to copy, say, this part of this column, paste it here, change its format, and sort it. So what I could do is record my keystrokes, convert those keystrokes into VBA code, and call it a macro and execute it anytime I want. So I'm going to go to Developer, Record Macro. It's going to be called Macro 1, and hit OK. I'm going to say copy this here. I'm going to paste it here. I'm going to change its, say, color, and say I'm going to go to data and sort it from low to high. All right. So what if you had to do this task every day or every hour? Well, since I hit record on the macro, I'm going to go back to my developer and hit stop recording. Now I'm going to just take this out of here just by copying over it. Now I can run that macro by going either attach it to an art object, or I can go to Developer, Macro. There's that new macro is created, Macro 1, and I can just run it. So there it's going to do that activity anytime I ask it to do it. If you want to see the macro, here's the actual code that was created. Looks like it put it in module 2. It created a module for you, and there's your macro 1. And here's the actual code. So it looks like the code. Let me magnify that a little bit. So it looks like the code starts with the word sub, macro 1, open, close. That tells it's a sub. Here's n sub. So here's some new code we've never learned before. Range B7 to B22. That's the range I copied. Dot select. So this must be the VBA code to select a range in the active workbook. Selection.copy. Oh, that must have been the control C. That's the code to copy. Range L7.select. That's moving my cursor to L7 and hitting enter. ActiveSheet.paste. That must be the VBA code to have a macro paste a copied selection. It looks like then here's an application cut copy mode false. I'm not sure what that's about, but this must be the code to color everything yellow. This must be the code to do the sorting. So you don't need to know how this code works, but this is the code. If you were smart enough, you could have written to do all those things, but it's just so much easier to record it. Now the other advantage to recording macros is, what if I'm writing a function or a macro where I know I need to do a sorting, but it's too hard to try to figure out how to write the code. What I could simply do is record myself doing the action. And again, you can think yourself recording a macro to run a goal seek or a sorting, and then you look at the code later and then you realize, oh, this is how I could set up code to do a sort, and then you can use that in other programs. So that's recording a macro. And the last thing I want to talk about is, if you're using macros, I just want to point out a couple things, and that is input box, message box, and range code. So here's a program. I already have it pasted in the start file. It's called payment, PMT, and it looks like it says loan payment equals, that must be a new parameter you're creating, application.inbox. So inbox must be a VBA function, and it looks like it gives me a prompt, and then I'm not exactly sure what this is about, but it looks like it's asking for a loan amount. And then it goes to range A1.value and enters in A1 in the current workbook the word loan amount, and then it goes to B1 and then enters the value of loan amount, which someone just inputted based on some prompt. And then it's going to ask for some other stuff using input box. So basically it looks like input box is a way in which the macro can ask a user for information, and then the range can put it somewhere. In the end, it looks like this program does a payment calculation using the application.payment function. Looks like it uses this strange code of application.worksheet function.payment. I don't think that's actually necessary. You probably could just use application.payment. And then it looks like it takes the interest rate divided by the loan term and the loan amount, calculates a payment of a loan, and then this message box, that looks like it's code to tell the user that the monthly payment is, and then just grabs the value payment and finishes off the sentence. So let's see how what this program does when it runs. So I'm going to go back to my workbook. I'm just going to go to this blank area here. The program is already in my function. It's in module 1. Here it is. And I'm just going to execute it. I'm going to go to data. I'm going to actually screen this. Let me zoom in a little bit. I'm going to go to developer, macro, and I'm going to run payment. Here's an input box, loan amount. I can put in, say, a $40,000 loan. Hit OK. There's the two range functions that put it in the spreadsheet for me. Enter the annual interest rate. Let me put in 9%. It just put it into A2 and B2. Annual interest, 9%. Term in years, let's do 5 years. Hit OK. And looks like it says, this is the message box, monthly payment is, and that's for the place for the value of payment. And you said OK, and the last thing it does another Well, it already did it for me. It put in the payment right here. So message box, input box, and range are kind of important ways to use macros to ask users, the executors, the person that executed the macro, for values. It uses those values then to place those values in a spreadsheet and tell you the user of a final calculation. So, in this topic, we talked about probabilistic or stochastic measures of worst case. We looked at earnings at risk, and also we used a Monte Carlo simulation to look at an entire distribution of possible outcomes based on randomness. We also created and recorded macros.